Welcome back to this video on Structural Analysis 2. Today we will focus on determining influence lines for indeterminate beams. Our task is to draw the influence lines for the reaction at support B and the support moment at A for a propped cantilever. As we have computed influence line ordinates for reaction at B in last video, here we will also compute these coordinates at 1.5 meter intervals for support moment at A. To find the influence line for the support moment at A, we utilize Müller-Breslau's principle. First, we remove the capacity to resist moment at A by introducing an internal hinge. Next, we apply a unit moment, MA equals 1, at this hinge. By taking moments about support A, we find that the temporary reaction at B equals 1/12. Under this configuration, the beam deflects. The influence line coordinate at any position x is defined mathematically as the ratio of the localized displacement, yxa, to the rotation at the hinge, theta AA. Let's calculate these values. We set up our coordinate system measuring x from the right support, B. The governing bending moment at any section is mx equals rb times x, which translates to x/12. Integrating the elastic curve differential equation once yields our slope equation, introducing the constant c1. Integrating a second time provides the vertical deflection equation, introducing a second constant, c2. Applying our boundary conditions, 0 deflection at support B, where x equals 0, and 0 deflection at support A, where x equals 12. We solve for our constants. This results in c2 equaling 0 and c1 equaling 2. With our constants determined, the explicit equation for the deflection curve, yxa, is established. To find the rotation at A, denoted as theta AA, we evaluate the slope expression at x equals 12 meters. This calculation simplifies nicely to -4 over EI. Now, we substitute both expressions back into our primary Müller-Breslau ratio. The flexural rigidity, EI, cancels out perfectly from the numerator and denominator. This leaves us with a clean, final polynomial expression for the support moment influence line. MA equals x cubed / 288 minus x bar 2. Finally, we substitute our 1.5 meter intervals into our derived equation, moving from right to left. At support B, where x equals 0, the coordinate is 0. As we move across the span, the negative coordinates grow, reaching a peak negative value of -2.285 at 7.5 meters from support B, before returning to 0 at the fixed support A. Plotting these values gives us the complete influence line diagram for the support moment. This curve visually demonstrates exactly how a moving unit load affects the internal moment at support A. Thank you for watching this video on structural analysis.